Let's look now at a more complicated of static equilibrium. Here we're actually going to be looking at a problem that involves two dimensions. Here's the problem. You have a 5-meter long ladder that leans against a wall, pictured here in the figure. We have friction and the normal force, which keep the ladder from moving around on the ground. We're going to indicate friction as Fcx and the normal force as Fcy. This being the Fc here would be the total force of the ladder on the cement ground. So that's why it's Fc. X would be the x component, which is friction. Y is the y component, which is the normal force. There you go. Now, okay, if the ladder has a mass of 12 kilograms, we want to find friction, normal force, and we want to find the total force that the wall exerts on the ladder. We want to find all of these. Okay, so before we do anything else, we need to figure out some angles here. For example, here, let me get a different color. The ladder makes an angle that looks like this with the floor, with friction. And it makes an angle that looks like this with the normal force. And an angle like this with weight. And so you see we need some angles in here. So let's see if we can find some of these angles. What we're going to do here is look at this triangle right here. Now we're going to find that those angles in that triangle by following the law of similar triangles. We have two similar triangles here. So the angles in both of these triangles that I drew are going to be the same. So if I have this triangle like so, we know that this is 4 meters high because that's in the picture. And the problem tells us the length of the ladder, 5 meters. Now, hopefully you recognize that this is just a 3, 4, 5 triangle, meaning that that bottom length is 3 meters. But we don't need that right now. We want to find this angle theta. And we know the side opposite, and we know the hypotenuse. Therefore, the sine of theta is going to equal opposite over hypotenuse. Therefore, your angle is going to be the inverse sine of 4/5. Plug that into your calculator. 4 divided by 5, take the inverse sine. You get that you have an angle of 53.13 degrees. So I'm going to go ahead and put that right in here. Which means any of these angles, like this one right here, or law of parallel lines, this angle right here, both of those are going to be equal to 53.13 degrees. What about this angle up here? We're going to need that because that's going to be this angle and also this angle. Okay, so we need that. Well, how do we find that? Well, we know that those two angles have to add up to 90 degrees. So I just subtract that angle from 90. And that would give me here 36.87 degrees. Okay, so we have all of those angles. Good. We're going to be using those through the problem. But now we need to talk about the method. How are we going to actually find these three forces? Well, one thing we do know is that this ladder is being kept in place. It's not moving around. Therefore, it's in static equilibrium, which tells us two things. That the total force has to equal 0 and the total torque has to equal 0. But since this is 2 dimensions, this breaks down into sum of forces in x and sum of forces in y. Okay, let's start off by looking at the sum of forces in x. What forces do I have in x? I have friction, and I have the force of the wall. Now, I can't do anything more here. I'm stuck because I don't know either of those values. So I'm going to put that on hold for now. Let's go to our next equation. Sum of forces in y. And that has to equal 0. What forces do I have in y? I have the normal force, Fcy, and I have the weight of the ladder, mg. Well, fortunately for me here, I know the mass of the ladder, so I know the weight. I can solve for Fcy right now. Which is going to be equal to mg, which is 12 kilograms times 9.8 meters per second squared. So my normal force would be 12 times 9.8 gives me 117.6 newtons. Okay, so there we go. That's supposed to be a check mark. I've got one solved already. So I still need to find the 2 in that first equation. All right, now we need to do the third. We're going to work with torque. Sum of torque has to equal 0. Now, to do torque, the first step is to find a coordinate system that will be to our best advantage. So if I choose, for example, up here, then Fw is canceled out of my equations. Why? Because the distance from the pivot to Fw is 0, therefore there is no torque. I could do it here in the middle. If I do it in the middle right here, then that cancels out the torque due to the weight, but then I'm stuck because I still have torque due to the wall, torque due to the normal force, and torque due to friction, so I still have that. The third option is to do it down here at the very bottom. In that case, the torque due to the normal force is 0, the torque due to friction is equal to 0. Okay, so you've got 3 options. Which would you choose? Well, the middle one you'd have a hard time with. The top one you would work perfectly. I'm going to choose the bottom one because then I'm canceling out 2 torques. So I get torque due to the normal force, torque due to the frictional force, torque due to the weight, and torque due to the force on the wall. All have to equal 0. Torque due to the normal force is going to equal 0 since it is at the origin of my coordinate system. Torque due to friction is also going to be 0. Now, the torque due to the weight of the ladder, it's going to exert a clockwise or negative torque. And then torque due to the wall is going to exert a positive torque. Therefore, the torque due to the wall has to be equal to the torque due to the weight of the ladder. Okay, so now I have 2 equations here. There's the one from torque, and here's the one from force. I can use these 2 to help solve for friction and for force of the wall. Well, if you look at the one on torque, I only have the force of the wall in that equation, so that's the one I'm going to work with right now. So we know that torque of the wall has to equal torque due to the weight of the ladder. Torque is calculated as Rf sine theta. So the wall, I'm going to be dealing with this angle, which by parallel lines is the same as this angle down here, which we found back here to be 53.13 degrees. So this is going to be radius to the wall times force of the wall times the sine of 53.13 degrees. And that has to equal the torque of the weight. Now the weight's angle is going to be this one right here, which is going to be the same as this angle right here, which would be 36.87 degrees. So Rm times the force, which is just gravity, times the sine of, I already forgot, 36.87. All right. So we want to solve for force W. So if I just divide by RW and then I divide by sine of 53.13, whoop, this one's going to be 36.87. And then we divide by sine of 53.13. I'm there. All right. So Rm, how far away is the center of mass from the bottom, from our pivot point? Well, the matter is 5 meters long. The ladder is 5 meters long. Therefore, its radius is half the way. Therefore, 2.5 meters. RW would be the distance all the way up here to where force FW is applied. So that would be my full 5 meters. Times the mass of the ladder times G, oh, not kilograms, meters per second squared, times the ratio of these two sine functions. So plugging this into the calculator, 2.5 divided by 5, multiply that result by 12 times 9.8. Then I have to multiply that by sine of 36.87 divided by the sine of 53.13. I get that the force from the wall on the ladder is 44.1 newtons. Okay, so far I have that the force due to the wall is 44.1 newtons, and we saw that our normal force earlier was 117.6 newtons. All that's left is finding the value of friction. Well, remember we have one equation we haven't used yet, that the force of friction minus the force on the wall is equal to 0. Well, that's pretty nice, because then that tells me that the force of friction has to equal the same magnitude as the force on the wall, just opposite directions. So there I have it. I have now finished this long, complicated, two-dimensional static equilibrium problem. Not too bad, was it? As you go through your homework and work through other examples, I highly recommend you go through the examples that are in the textbook. Feel free to send me any questions you may have. I'm happy to answer them, to kind of give you some tips as you go through this.